Hello everybody, welcome to another stream. How's it going? Hey there Akras, welcome, how you doing sir? How you been? So last stream, we got the Froxel based binning working, which was super great. So now our spheres are binned into frustum space inside these 3D bins, right? 3D cube bins in frustum space. So we've got 3 acceleration structures which we can test when it comes to accelerating rendering tons of spheres, right? So what we want to work on next is a camera system. Well, not really a camera system, we just want a camera and be able to fly a camera through the world. We also want to set up multiple instances of models, right? Make some models and have multiple instances of those. So we basically need a way to translate, rotate, and scale between spaces, right? So we need basically a 3D matrix, but we're doing a bit of a. Sorry, I'm just going to chat up on my phone at the same time. So we're currently doing a, the standard sort of, 3x4 with an implicit row at the bottom. So it kind of makes it a 4x4, but with 12 floats instead of 16 floats. And so we wrote this guy up last stream at the end, but it still needs testing and it still needs completing because there's a few functions that there's a few ones that we want to add for completeness. And that is like inverting a matrix, and we've got a bunch of convenience functions which allows us to create. See, doing a rotation matrix is actually a lot more work in 3D. You need kind of 3 separate ones, right? And then you need to multiply them together. But there's a way to sort of basically reduce that or heavily simplify it down into a single function. But the order does actually matter. So we probably want to create different swizzled versions of this function, which is simplified. So we're going to start with this today. And if we get any more time, we'll start on the camera, the free cam. Should be pretty cool. What camera? Smooth, of course. Demonstrate's going to be smooth. It's not going to be fixed. It's going to allow us to move and look around, because we want to be making a nice 3D scene, so we want to see all of our lovely models and test performance and all that stuff. So yeah, it's gonna be good. Hey there, Egotists, welcome. How you doing? How's things going? So first we just want to test this all out. Bye, my friend. 27 months. Thank you so much. Appreciate it. How you been? How you been? How's it been going? So we just want to start off by simply transforming a simple vector and just set up a couple of prints, basically. It's not anything too complex. We'll just chuck it in here. We'll block it out so we can just delete it, right? Because test code, you have to maintain it, and it sucks. So we just delete it when we know the code's perfectly fine, and done. Hey Zen, how you doing? Awesome, good to hear you, Egotist. I hope you guys are looking forward to the holidays, December. What we're working on today, we're testing out a basically a 4x4 matrix. That we've handwritten, and we're going to test out the code we wrote last stream and continue and just basically complete this so we can have a nice camera and make multiple instances of models and stuff. So this is going to help us achieve that in the future streams. So we should hopefully be able to ace this today. So it's a column major 3x4 matrix with an implicit 0, 0, 0, 1 row at the bottom. But how's things going? How's things with you, Zent? How you been? Finally moved into a new place. So much stuff to do. Exactly. Yeah, I know what you mean. Did you have a lot of stuff to move over? See, I had the benefit of moving from my parents, and I didn't really have a lot of stuff. So it was just, come into a new house and just fill it. Basically, we had a problem just trying to fill it. We've still got rooms to fill. But yeah, the most difficult piece was doing the mortgage, because you have to like sign so many documents, read through so many documents, and just make so many phone calls, and it's just so much work. Oh, so glad that's over now. There's a few things I don't understand how people do with like a full-time job. That is, buy or set up a mortgage for a new house or look for another job. They take up so much time, and I just don't know how people manage to do it. Like when they have a full-time job already, it's just so much work. How's Game of Energy come along? Pretty good. With do I have anything that runs? I should do. Voila. So what you're seeing is this scene rendered 3 times on top of each other, using 3 different. So they're all with ray tracing, but there's 3 different acceleration structures that we're going to be trying out. So we just got to the point now where we've tested out a few different approaches, and it feels like we need one acceleration structure which is specific for the view, so for the main screen, which has the most rays. And we need another acceleration structure. Yeah, sorry, one which is from the main view, so we can heavily optimize it from being from the coming from the main view. And the other, we probably need an in-world acceleration structure to do some lighting calculations, and that will probably use the BVH system that we made, which you probably saw. So yeah, we're just gonna be we're working on effectively building a test scene now, but we just sort of got to add the features to get there. So we need a camera system, we need to add multiple instances, and we need to support animated instances and static instances, and yeah, then we can basically just start tuning of these acceleration structures and just see which ones are the best, and just go from there. Ready? Yeah, it's gonna be awesome. So BVH was the best one of the ones you tried. No. The best one was the screen space tiles from this specific view. But the problem with the screen space tiles is it doesn't allow you to accelerate. It's not very good from different. Well, first of all, if anything's off the screen, it's not cached inside the screen space tiles. So we bin them into screen space tiles or the spheres, and we have a little list per tile. Well, if it's not on the screen, you don't have any data for it. So the BVH is the best system that we have for stuff that kind of goes, which is not within the, which is not specifically for the view, the main view, which goes for other views basically. Like you might have a light. You might have a, as your view frustum, you might have a light over here, shining a light, and it bends, woohoo. And there's a sphere here. There's still shadow that gets cast in the view, right? But so we need some form of way of handling that. and that's what, like, you could just make the screen space tiles bigger and be off-screen tiles, but it really happens for like all over the scene. It can come from behind the camera to the side, so yeah, it's the best. Yeah, so it's not the fastest though, but we did a pretty good job optimizing it though. I was quite happy with how far we optimized it. We've also got to see how all this stuff scales out to like a big scene. That's still something we've got to see. Because right now we did performance benchmarks against stuff that was a very simple scene. So yeah, we've got to try and make it, you know, yeah. Make it do more. Right, so let's do like position in local space. And let's just do like let's just give it a bunch of zeros. And let's just start basic, right? Let's just try to translate, see if the translate works. And then we'll just up it from there. Hey, Wajilla, how you doing? Welcome, welcome, welcome. You know what? Let's actually stick. Should we do yeah, we'll do 12, 34, 45. Wait, is that a good idea? No, no, no. Right. Let's just make it go up. And it's normalized. Okay, so we're going to initialize this. How do we want to initialize it? Should we do the we'll just do translation first. I forgot, it's kind of like by value because shaders. Right, so we pass in, what we pass in? Oh yeah, so we need some form of translation. So let's just say, oh, it goes 10, well, let's do the thing, right, 12, 34, 45. And then we're just going to print this guy out. So we have a nice function for that. Call it world space. So do one of these boys in world space. That'd be yeah, multiply. So multiply a vector. This shouldn't have any translation applied to it, right? So it should just stay the same. So we pass in world from local, and then we pass in position local space. What we should see is position world space should just be the same because there shouldn't be any translation applied to it. Oh, we should do an exit. It would be great if the camera was looking at something at the beginning. Camera was looking at something at the beginning, so you could see the movement. Right. So you're talking about like following a would have been great if it followed the, maybe this isn't a good way of printing it. Like following the like the model that we had. Let's just print out like this. Problem is it prints out the whole union and it just repeats so much crap. Alright. Okay, so we got the local space one got 0, 0, 0, and the world space one got 0, 0, 0. That's what we expected, right? If we set it as a translation, but we did it with molv because that just says transform this as a vector, which means do the rotation and scale, but not the translate, right? But if we did the P version, what you'll find is we should translate. And we didn't. Bum, bum, bum. So I need to figure out why. Oh yeah, we're just checking if the maths is correct. Yeah, we're just checking to make sure that the maths is correct. We also have to change the way the shaders work when we set up the cameras, because currently we don't translate it into view space. We have to translate our stuff from world space to view space, the stuff that's binned at least. So we have to translate all of our spheres, wherever they are, into view space, basically. Is that right? Yeah, it depends. It really depends. When we're binning, it has to go into view space. Then when we shoot an array, I think we have to take our array from world space into object space, so the axis line bounding boxes are axis aligned. Because we'll have our model, which is comprised of many spheres. And why isn't this white anymore? Of a model which is comprised of many spheres, right? And maybe these guys are put into bounding boxes, right? Something like this. Now, if the camera's over here, right, and you shoot your array, boom. Obviously, these aren't. Oh, okay. Yeah, from the camera's perspective, these are not axis aligned, right? When you've got your vectors like that. So what we have to do is we have to translate it from that space into this space. So from world space into local space of the object. And, or view space, sorry, yeah, from world space into local space of the object. So these become axis aligned when you do your array versus box collision. Stuff like that. So you have to account for those things too. Alright, so this is an apply, which is a bugger. So let's investigate why. There's the translation right here, huh? So I feel like if we print out that lovely world from local, what we'll discover. Oh, that's not a good way to do it, is it? Doesn't let dump in that. Yeah, we dumped that translation. I don't think that's... Oh, it's right. We literally add it on to the end. Think you're working on persistent for the game engine. Awesome. Are you just in the keyboard controls? Are you getting the gamepads working? And what platforms are you doing on? So there's no multipliers happening here. Or a strut, that's good. CDO translation. Oops, again. There's some media motor-based event. Right. Event-based type stuff. Okay, interesting. Yeah, I've not seen anything like that before. So obviously what you're saying is like you'll call a function to say you're handling the how you handle the event, I guess, and it's in an immediate mode type of way versus polling it, right? It says, can you explain in short what are shaders and how? What are shaders? Shaders are basically like little programs that run on the GPU. That's all they are, but they're typically specialized to do certain things. Like the main one that people talk about is there's a thing called a pixel shader, where you basically color in a pixel each a little program that gets ran to color in a pixel, and you color in the whole screen, for instance, or whatever triangle wherever triangle goes over on the screen. Um, but yeah, for how we make them in our code, I have a little custom shader compiler which compiles C code to SPIR-V, which the graphics APIs use, and basically means we can share C code between the CPU and GPU. But I'm doing a bit of a thing this stream where I only use compute shaders. So compute shaders are like the lowest level building block of how sorry, they're essentially like the lowest level shader. You basically, if you understand the hardware, you can sort of exploit that, and you kind of when you write tons of compute shaders, you really understand the hardware because you can really um, take advantage of that and do some great things. So essentially, you just take advantage of the fact that there's so many threads running in lockstep, and you know all that. Well, technically not threads, but yeah. Anyway, that's about it. Um, are we even returning the right vector? No, we are, aren't we? I am so confused on why this doesn't work. Let me just do this, right? Oh, we didn't use point, did we? Or let's just do z plus that, right? And it should just be... Right, that didn't even work, apparently. How? Like, what is point dot z? Surely that's like 0, isn't it? Then I didn't use t. Damn you. Right, so let's say core unused point. Yeah, but that's how you do unused, man. What? What is happening? Alright, let's try that out. Yeah, something fishy's going on. Like what? Like what? So let's say just do a standard printf on this, right? F. Hey, not so red. Odilo, welcome. How you doing? You see? There's some extremely low level stuff, man. At some point, you might actually code games in assembly too. Not really. It's not really worth programming games in assembly, um, other than for a bit of fun and trying to learn assembly. But you can use aspects of it. There's like if you want to hand optimize some bits, um, yeah, definitely you can whack out some assembly, but I wouldn't program the whole game in it. How do you communicate the GPU with C? I mean, to make your own compiler, your own compute shaders and use yourself. No, no, no. I spent like a year and 3 months on the side working on this guy. So basically, it's just a C compiler on a restricted subset of C, and we just share. We've got like some restrictions right here. They are, but we have added support for like swizzling and printing in shaders and multiple shaders in a single file, which apparently is a big one for some reason. I don't know why this is not in other shading languages. Um, yeah, we've obviously got all the textures and atomics and stuff, and shaders, sort of thing. I'll just drop the link in there. So yeah, it's all proper great. Yeah, it's a really great workflow, basically. Oh, this is because my damn my compiler's trying to look at it. That's why. Ah, bugger. There's a bug. It doesn't like that knot. Guaranteed. Doesn't like that knot. You know what? Let's move out of there. Screw this thing. Okay, unless our transform is not. No, return T. What is going on, man? If not def. Yeah, that would have probably worked, innit? Right, something's definitely fishy. This printing then is just wrong. Float. It's casting it to UN. One T. Yeah, that's why it's the damn printing function. Yeah, I think we should go with that suggestion. Before. Yeah, so a silly thing about generics in C11 is everything has to be semantically correct, so the types have to be type checked, even though you can switch on a type. So, it's so bloody annoying. So if you put a float in, the floating point has to be valid for all of the other types, including the pointers and stuff. It's just silly. So we basically want to float out for a given pointer, right? Wait, what will we be taking in? Things it could be any type. And a pointer won't turn into a float. Alright, let's just not bother with this today. Let's just carry on with what's important. Well, worked at Facebook, Amazon. Yeah, I don't know what thing is really fully. Nah. I've not really actually bothered trying because I don't really want to work. I don't know, like, it just sounds like proper cringe to work at Facebook or Amazon or Google or whatever. You know, you probably get paid well, but it doesn't really sound fun. Right, okay, so let's just whack out the standard printfs then. Damn it. Let's just record a macro. Okay, so now we won't be lied to by our own functions. That right, so that translates. That's good. But we put a v there, this should be a vector, so it shouldn't translate. So these are definitely right, are they? 12, 30. When the original had a 1 in it, that should be 35, right? So we need to actually revisit that one. But let's just check if the vector one moves. Okay, that's fine, right? 0 is the exact copy of that one, right? Let's put a split in between here or something. So we can actually see a separator between it all. Cool. So, oh. Voila. So we put P back in here. This means it's a point, so it does need the translation applied. But it's not applying... Oh, now that Y... Like, I should be expecting it to be adding... Adding that 1. Right, because it's coming from local space with a 1. And we're adding this translation of 12, 34, 45. So it shouldn't end up on 12, 34, 45, right? So I think that's off by 1. So your axis vector, this is... Right, this would be 0, so this won't get applied. This would be 1, so it should be 1 times 1, right? Oh, sorry, I've just nuked my... I nuked my thing, didn't I? Okay, let's put that back. Right. There we go, it says 35. 12, 35, 45. Excellent. Excellent. So, we can now... We're now seeing that the multiply... Yeah, so we know the translation basically works, right? So let's do some scaling. Um, so it should be scaling on the yeah, only on the Y, right? And it should obviously work for the V as version as well. So it's just doing 30. So it's doing 1 times 34, and it's only keeping that, right? It should probably have some more values in here. So it's doing 2 times 12, 24, and 3 times 45, which is 135. That makes sense. So that's not bad. We obviously want to do a more complex one, but let's just do a rotate. We'll do a rotate X. So if you've got, so along the X axis, right? So it's along that one and you're rotating it, which means you should move the Y. Wait, what would it be? Yeah, the Y and the Z would just get changed, right? Whereas the other ones won't. Whereas the X won't. So let's put an angle. Am I going to do quaternions? Not yet. I'll do quaternions when I need them. But yeah. The thing is, I'm not sure. Yeah, the thing is, I don't know. Is do you get the gimbal lock if you essentially produce a matrix? Like if you have if you produce a matrix from like Euler angles, right? And it's like a small little adjustment in the rotation. And if you like keep applying that to the camera matrix and keep rotating it, do you get the sort of gimbal lock? I'm not sure. Right. But so if I end up needing it, I'll do quaternions. Yeah, the maths kind of does go over my head a bit with quaternions, though, to be fair. I still need to kind of understand those guys. Right, so the gimbal lock comes from the rotation axis being co-aligned. No, not with quaternions. So say if you have like the camera matrix, right? You have your sort of your sort of view from, wait, what would it be? Oh yeah, your view from world, right? And then say if you produce like from your input, like this is something that you just have persistent. Let's call it static then. And then every frame you produce a sort of like input rotation or whatever. Say if you've like moved the mouse and you sort of add a tiny bit of rotation. If you were to sort of join the, apply it to this one and multiply it, would you get a gimbal lock? Is that because then it's essentially coded in a vector, axis of rotation, and rotation around said vector. No gimbal lock. Yeah, I understand that. Oh, okay, so you've got like a vector and how much it rotates around it. Interesting. Right. Huh. Matrices or quaternions don't really matter for gimbal lock. Any set of rotations in 3D can be applied together and represented. Yeah, so I know you definitely get a gimbal lock, right? When you have a vector, right, that represents a form of rotation and you keep applying to that, right? This is where you get the gimbal lock. But how I'm curious is like if I were to somehow build, just have some form of like, mouse dot x whatever times dt and build some, and then apply this to the persistent camera matrix. I don't think you get a gimbal lock, but I could be wrong, right? And that's what I don't know about. Right. If you were to multiply these two together, would you get a gimbal lock over time? Not just rotation x. It could just be rotation across any, whatever. It could be. Could you get gimbal lock? That's what I don't know. Right. Basically. Right, so when we rotated this guy, we said along the x-axis. Oh, sorry, on the x-axis, so we would have just gone like that. So we said rotate it by 1. Yeah, so we did like half pi. So 1.6, something like that. Okay, so that's gone from 1 to nearly 1z. Yeah, which is in front. That makes sense. It's gone the right way. Gone in front. So we did that, obviously negative, and then did full pi, it would be 180. Yeah, that would be backwards. Yeah, that makes sense. Negative there, good. Yeah, so that one works fine. Let's rotate along the y. So rotating around the y isn't going to do anything for us there. So we should already have a z vector. So if you have a z, rotate along the y, we should get positive x. Yeah, positive x, basically. Good. Right, then let's do the z. So for a z, let's have it looking down the y again. So that you want, so positive, let's do it on the x actually. So positive, we'll bring up to the y. That went down to the y. I'm not sure if that's what I want. So I think I got the signs the wrong way around. Gimbal lock is when you're doing Euler angles when two axes of rotations align. You need to keep in mind if you're rotating around camera axes or the world axes, right, you can produce, okay, so I need to translate it back, rotate it and put it, something like that. Yeah, I think I know what you're saying. If you can produce a matrix that does a rotation around an arbitrary axis, and you keep adding rotations like this over time, there is no gimbal lock because there are no Euler angles. Right, gotcha. Yeah, so it comes from the fact that you're applying it to a... Yeah, got it. Yeah, so I'm not sure if I already need the quaternion, right? A quaternion is great if you just want to store rotation. until we need that, we won't be doing quaternions, basically. Yeah, that got negative. That's not what we want. So we changed the signs on the sign. Got positive. Perfect. So it rotated it like that. So it would have been over there along the z-axis. It'll rotate it. Go up. Cool. Okay, so that's our rotations, scales, and translates looking good. Now what we want to do is essentially create two of these, right? Combine them with a multiply, and then translate it between the spaces, right? So we need to do something dead simple that we can know the output. Oh yeah, that's another good point as well. They interpolate better, isn't it? I forgot about that one. Yeah, isn't it like slurp and stuff like that? So if you like animate, right? Yeah, yeah, so interpolate better. That's a good point. Yeah, we might have them for that then, I guess. Um, okay, so what's the other ones we need to do? So if we combine them together, like we have a nice handy function here, which just computes it from all of these, but we do want to make more of them where they do the x and y's in different orders. Potentially. Yeah, so let's just test this produces something that we want. Then we'll produce two of these, and then combine them together with multiply, and then translate a point or something and just see how it behaves, right? So we want to produce, so translate, rotate, scale. Really should be the other way around, right? Really we should do SRT, because that's the way it's applied. So scale, let's do like probably need one or two, fair play. Yeah, it might be a good way to save time, right? So if I were to say 12, 34, 45, and then let's do like a 1, 2, and 3 here. Let's do 3, 2, 1. What do we produce? Let's just double check that. That's not right at all, is it? Oh, yeah, I think the way we generate this ended up wrong. Maybe we should relook into that. Like, if we kept these all as ones, what do they do? Right, still doesn't work. But what I guess translation is just there on the end. Oh, my mistake. More P. So we stick these all ones. So it's going to scale it by so times this by 3, this by 2, this by 1. Right, so you get basically added 3, added 2, right to that. And then to these numbers. Okay, so you get 15, right, that's good. Added 2 to there. Yep. Added 1. Good. So that's looking like it's working fine. Although there is the translate. If I did like MPy divided by 2, I think that would have on the Z axis, it wouldn't have been right. So that was translating the one. I need to, so scales, let's do the V version so it gets rid of the translate. So I can see the numbers. So you're positive 3. That ended up correct. That ended up correct on the Y, that's good. Let's move these around. Translating around the, so that should make it from the X to Z. Positive Z, very good. And one more time. So rotating around the X-axis, which means we've got to do something different. So that would just be making it positive, positive Z again, actually. Negative Z, bum, bum, bum. We need to flip something, that's not good. Right, so somewhere in here it's going to be wrong. Shoot. So this isn't like, what is it getting wrong with the signs? So if it's the Z trans, sorry, which one is it again? It was the X translation. So the X puts its things in here. So the negative, that would be negative. That applies to axis 1.z, but the axis 2.y should be negative instead, right? Here's the X one. Yeah, that's Y. That's it. So, no, it's X. X. SX. Yeah, I just need to flip it in general. No? No? It doesn't multiply. Yeah, it's the sign, isn't it? I might have not been S. So. Oh, I'm on the wrong one. Rotation, transform, 3D. Right, that's why. Right, that worked. Put it into the positive there. Good. Right. So that's great with, like, this thing works, which is cool. We want to now add like, thinking about it then, that rotation transform one, which, let's just make sure that one's got it right as well. Yeah, that's a -1 there. So that needs the same treatment. Obviously, it comes from the same code generator, so it's going to have that same problem. Oh, there we go, +1. Looking good. So, okay. So now let's create two transforms, do a multiply. So we'll have our world view from world. So we'll create a world from local and view from world, and we'll combine them to make a view from local. So we need something simple that we can sort of calculate, but also be a good enough test for the multiply itself. So for this one, hey host man, going good man, going good. Just getting the 3D transform code all tested before we start getting a camera in, basically. So we just started writing it yesterday on Sunday, and today we're just testing it and finishing up really. But yeah, how's things going with you? I've got like 3 days left to work, and then I'm off for 3 weeks, off for the Christmas break. It's gonna be good. So should we do? So from local space to yeah, so we should probably add, oh, what's an easy way to do it? Yeah, let's just do 90. If we do 90-degree turns, I'm not sure. What are we rotating around? Um, hmm. Am I stream view during my vacation? Yeah, I'll still probably stream most of the days. Probably around Christmas we'll do something a bit different, I reckon. But in terms of the regular stream times, they'll still be the same. So probably as soon as the holiday starts, which will be from next week, I'll probably do the standard, 6 p.m. GMT till whenever I go to bed for the Tuesday, Thursday, and Sunday. But on the Christmas week, yeah, Christmas week will probably be a bit different, but it might mostly be the same. Yeah, we'll see. I'll post the sort of updates as I'm gonna know in the Discord. Um, yeah, it's interesting how many people like actually stream on Christmas Day and stuff. You know, you just would think that people like everyone sees family and everything, but people actually sit down and stream on Christmas Day, and that's quite crazy. Um, mhm. um, yeah, so we rotate around. Um, yeah, so what way would I rotate? So you have the view from world, and you're rotating 90 degrees, say. Um, hmm. Like maybe we. So I want to test that rotation, but in the multiply. Or maybe I don't. Oh, I kind of need to. Um, so if you rotate the view from world, let's toss it into the renderer. Nah, not yet. I still needed the invert. So imagine if your world space is here, starts from here, and your view space is here, right? There's your view frustum. There's your view space. Um, like it's maybe if you translate it. Oh, yeah, I'm not sure how it would actually be. Hmm. Yeah, sod it. Let's not do the translation. I can't think of a good test for it. Let's just move on. I can think of the scaling though. So to scale from, let's give this uniform or whatever. There you go. So essentially, you're just going to scale 3, 2, and 1. Right. So you're just going to scale these guys. Um. Is that right? It's also not as simple just to toss it into the renderer. There's a bit of work to do. I got to change a few aspects, but we can definitely. Oh, shit, it's the wrong way around. Right, so line those boys up. 3 arguments. No. Okay, so we got this guy now. So position multiply point in view space, please. Alright, so we should just be scaling it. That seems legit, right? 3 times 12, 2 times 34. That's 2 times 35. What's going on? This one is... Huh? Why is the y literally off by 1? Or 2, rather. So we did it in world space again. That's how I could have tested the rotation, is I just translate it manually. And then just compare the two. Right. So it's 35 when you translate it into... Why? Ah, because it's got the 1 there. Of course. Of course. That makes sense. Right, so I guess we just want to have 2 view space ones. And this one's going to translate the world space. View from world. Right. And then we just simply apply some form of rotation. And if they're both the same, then it means the multiplier is correct, right? Okay, they're both the same. Ta-da! That's good. Yeah, so this view space one is going from view from local, so that's the combined matrix. This one is the view from world using the world space position, right? And put that into there. Cool. So we've gone and tested all of the functions that we added basically, which is pretty good. We want to add one more though. We basically need an inverse function. We could probably add these as Rosmusko was saying, as when we need them, different rotation orders. So an inverse function, I've already got one of those in HCC. See, HCC, which is my C to be a V compiler, has a maths library, and it has a bunch of like matrices and stuff, but I've not really ended up using them for this project, and I don't know if they're a good idea in the long run. Like, the vectors are fine. It's just the matrices, like, you could probably do with like an implicit row, basically. And save yourself 4 floats or whatever it is. So the bit I don't know about is if we do this, yeah, you should be able to invert one of these, no problemo. So here's the code. Right, let's just copy and paste it over and see how well it works. So just replace this with transform 3D. We've obviously got to adjust all those things. It can be a bit of a ball ache, but we'll get there. Cool. So we can actually just do find and replace on all of this, and it should just be pretty simple, I think, to do. Yeah, we've got to manually translate all of them. There's column. Well, it's not necessarily column major, but yeah. The thing we can do like dot or something like dot cols 0. I think you have to put backslashes around these guys. Yeah. So you replace that with dot axis 0. I think you can do that for basically all of them except for the third one, because the third one is just no, you can do that for all of them. One, I maybe didn't need to do it like this, but okay, it's fine now. It's very quick and easy. So 3 is actually just translation. Now there's a W component in a lot of these, which should now needs to be made into the implicit values, right? So you've got 0, 0, 0, 1 for the final set of W's, right? The final row. Yeah. So we need to just have that. So we might as well go and encode them. So you have the implicit row 0, 0, 0, 1. And we can just simply just instead do I row yes, column by column. Right, so this would be yeah, remove the terms with non-zeros. There, I could do that. I was thinking about keeping it though, so it could be better to be optimized away. But yeah, possibly. I guess so. Let's just remove it. Yeah, you can heavily simplify the crap out of this, can't you? So this one all goes, right? Because this is column 0 and 1, which, the only one that has 1 in the end is translation, is basically the translation one, right? So that one can go, which means S2 is gone as well. Like, all these have just gone. Wow, this greatly simplifies the whole bloody thing. It's in your C's. This one is kept. This one is nuked. Pretty bananas. This one is nuked. That one's nuked. This is then replaced with that because it's basically times by 1. And then we now have, right, oh my days, it gets heavily simplified. So where's S2? S2 times, so we get rid of S2. Then we get rid of S4, 5, 6. What? S4 and 5. Yeah. The whole term that includes S2. Yeah, I think we just get rid of that, right? So now what we should do is reduce these down to 3 probably. Yeah, we did get rid of the whole term S2, I think. Right, and okay, maybe you're a little bit lagged in the stream. So now we just need to bring S3 down to S2. That was pretty cool. Right, so we have to do that again. This is pretty sweet. So, yeah, so the way we know this works is if we inverse a matrix and then translate those examples back to local space, and then that'll just be it. That'd be amazing. Right, so we'll do this again. Oh. I've already done the hard work. Let me go and get this. Okay, so this one, so we basically brought 3 down to 2 and got rid of every other one on the S's. Okay. Alright, maybe we'll keep that because I've already done it now. Okay, so what do we got here to sort out? Right, so all those W's. So should we get rid of the W's first and deal with the S's in a bit? So this is times 0, so that all goes. This is another times 0, so that all goes. This W simply doesn't exist, so that's this whole thing goes. This whole thing goes. This whole W disappears. So does that one. This one ends up being a 1. So you just get rid of that. Because no multiply 1s, right? These whole W's go. That's multiply 1, so we get rid of that one. This whole thing goes because it's times by 0. Oh, this whole thing goes because it's a W column. Get rid of that W column. Sorry, W row in the column. Now we're just left with the S's. So the S's, it was an array of 6 that we need to delete the 2, 4, and 5, and then bring 3 down to 2. Oh, I do have a W left. Thank you. I see now. So that's an implicit 1. We delete all the S2s, which would be 0, basically. We just delete those. S4. So that's a 0. Delete that. And an S. Oh shoot, did I do something wrong with these S? Right, I did something wrong there, I saw it. Alright, we'll start again with the S deletions. I just realized we've probably buggered up this we might have buggered up this determinant thing. Because if that multiplied the S2 with a C2, the C2 should be getting rid of as well in this expression. I don't know though. Because it would be... Yeah, compare one from the compiler source. Yeah, I'm not sure though. Like, the thing is like, if we get rid of... If we reduce this... So if we get rid of this whole one... Oh yeah, because that would have been times by 0. Times by 0, so this would just be... implicitly be 0, yes. Yes, that's correct. So... we actually did this wrong on this determinant thing. Okay. Let me bring this back. And we'll redo it. Then we'll copy it over. So it's S2. That is 0. So you need to get rid of the multiply. Then it was S3 you keep, S4 you get rid of. That's a multiply, so get rid of that. Damn it. Minus that, so you get rid of that one. Plus, and then you get rid of this one anyway. Right. That'd have been S5. Then you bring your 3 down to 2. And that's why I saw another S2 there. Okay. So I didn't need to get rid of that one. But in terms of what we need to keep here, the C's actually need to get rid of as well. The C's that we don't need. Right? So we don't need C... Alright, let's write this down. Remove S2, S4, S5. And then for the C's, we don't need C0, 1, and 3. This is a lot of simplification. Look how many less instructions you have. This is great. I did not realize there was this much. Yes, this means we can get rid of... We can just do that. And then the... Is that right? So you got the C4, 5, and 2. Yeah. So the 0, 1, go. And the 3. Then you bring these down accordingly. Whoa. That's crazy. So 5 becomes 2. 4 becomes 1. And the original 2 becomes 0. That'd be pretty dope. So let's fix this up. There's the determinant fixed. Now we've got to sort the S's. So we need to remove S2. So S2's got to multiply against something else, so we get rid of that whole thing. There's a plus followed by a minus. So it should just be the trailing one. Ugh. We also need to get rid of S. What's any more S2's dot about? Wait, which one do you keep? Yeah, you can say plus that, then minus that, yeah. There's an S2 there. No more S2s. The next one is S4s. Wow, this is heavily simplified. I did not realize it was this much. Right, S4's done, S5. Oh, that translation W is still there, that's fine. Because that's just 1, so we just get rid of all of that. Because it's just 1 times whatever, so we just keep the whatever instead. There's some more S5s dotted about. It's alright, that's times by 0, so you get rid of it. Minus that though. 0 minus this means negative that, right? Crap. We might have to quickly double check some of those, but it's fine. Yeah, crap. Okay. Yeah, we'll double check it. Yeah, let's just finish it up then. Okay, so any more S's other than S zeros? 3s. Okay, so you just bring the 3 down to a 2. Okay, so now we've got to do the C treatment. We heavily simplified the C because we don't need them to make the determinant. Wait, we didn't need them to make the determinant. But we need them in here. Yeah, but you need them in here. Yeah, they were cancelled out in the determinant calculation, but they're still needed in here. Okay. I think that's right. So, inline C0, sorry, C array. I'm not sure what you mean by inline. Oh, the ones that just aliases. Ah, good point. Wait a minute. The duplicate aliases of what? Ah, I see what you're saying. Yeah. These guys. Gotcha. That's a good point. Let's just quickly double check something. I think I buggered something up with the negates basically. So we kept S2, which is actually originally S3, right? So where's the S3 in here? Can the S3s? Right, so that was on, so we get rid of this one. That S3, that was a plus here with all this other stuff, which was just cancelled. So this is fine. This one here, where's your S's? There's no S's involved. Right, so we kept them all. That's fine. Okay, so let's quickly double check the other guys. So delete the W, any of the S's in here. There's some S1s at the bottom. Wait, S1 stayed in S0, but there's an S2 there. So this got cancelled. Right, saying plus. Yeah, but we kept the minus, wasn't it? Oh yeah, and the 5 got deleted. Oh yeah, but we kept the minus. Because you just would have ultimately said 0, take away that. Right, okay, that's fine. That's good, we caught that one earlier, because otherwise I would have missed it. Then, this is this one here, this column here. So there's no... The S's are on the bottom one, yes again. So S4 got removed. S2 got removed. And there's ultimately a plus there. Okay, that's fine. Okay, so then you're left with the final one, which is the translation column. So the translation column, you obviously get rid of the W. You've got your S here. Yes, these are the S's you kept. 0, 1, and 3. Okay. Very good. So to me that's fine. All we've got left to do is translate this, do that alias removal, right? So we can actually move this down to 3 here, delete these, or replace C2 with, you know, the compiler should probably do this. There's so many of these. T-axis cool. C4s T-axis 2 dot Y, and then C5s T-axis 2 dot Z. Okay, so that means we've got yeah, now we just got to move 3 down to a 2. Okay, that should be it. Pretty crazy, that's a big reduction. Like, I didn't realize it would reduce that much. That's pretty sweet if it works. So it's time to try it out. So what are we doing exactly? What do we want? Yes, essentially what we want to do is translate it back. So on like a local space 2. And if it translates back, that'd be pretty stellar. So inverse, transform, 3D. Now we want to go from take the view from local, and if you invert that, it's local from view, right? So if you take one of those view space ones, it should put it back into local space. And we'll find out. This would be amazing. No. Oh. It's a little bit off. We should be seeing 0, 0, 0. Check that you get an identity matrix if you multiply an arbitrary matrix with its inverse. Ah, interesting. Yeah, I think we're just off. Yeah, I have to write more print code. I'll do that test after I get this one working. That's a good point. This one should work, but it's not. Just got to analyze why that is. Right, I'm just gonna fill up the drink. I'll be right back. I just realized something. I want to double check that this one actually works, right? I could have swore I tested it. I tested it, right? But maybe I didn't. Um, so let's quickly see what we can do. Columns, final column, right? X. Right, what are we gonna do? Let's just do your sort of right, let's do 0. Let's just do a bit of scale and a bit of translation. And let's just see if we multiply something and bring it back. Does it work? You know. So we'll do like a hey, we'll scale you by 3, 3, 4, and 5. So it's y, z, 1, 2. So that's the diagonal, right? Nothing too complicated. And the final column x, y, z. Right. Let's just do the whole sort of 12, 34, 45, and we'll just do a y and a z, right? Now, if we multiply a point, mol f32 times 3. Yeah, which way around do you want to do it? I think it's, because it's column major, it's, yeah, f32 times 4 multiplied by that, yeah. The proper matrix thing. So, you put the m in, then you do a, so let's say we're on 0, 0, 0, and the one column, or the W column or whatever, is going to be a 1, so it's treated like a point, right? We apply the translate column. We'll call this like pos t for some reason. Should always need a t. Right. So the test is that we essentially want to do a pos n for some reason, because I don't know, whatever. Now it's going to invert m inverse before we do the multiply again with pos t. Cool, so let's see how we go. I'm not sure what pos t w would be, so should we print a w just so I can see that? I don't know, I think did it retain it? Okay, w got retained. And it did go back to 0, 0, 0, right? Let's put, okay, with as gotten odd was saying, with some precision errors, right? As we see there. So let's just quickly do something different. And we got that, okay? So we know this works now, the code that we copied, okay? So let's just apply that same test. Yeah, let's remove the rotation. And let's see if it's because we did the rotation. Right, we got an AN because I guess it wasn't an invertible matrix. Was it not an invertible matrix? So we've got an AN or something like that. Yeah, so if I did a little bit of rotation, it worked. I'm not sure why that is. Okay, try printing the matrix. I'll give that a go. Unless, oh, it's invertible unless you scale 0, right? Yeah, it could be the way we've made the determinant or whatever. When we've heavily simplified the code, I think we might have buggered something up there. Okay. So what you're saying is look at the scales, right? I just want to be lazy. View from local dot axes x and then a z. Okay. The scale is still 3, 1, or 2 and 1. So it might be something to do with Also tells us the same thing, fair play. I haven't got any rotation though. Turned off the rotation for now. Yeah, I think I did something wrong in the determinant thing, maybe. So we did double check this, right? That we copied over. This is the one that we copied from. So if we take this and bring it back over again, remember we end up simplifying and removing these guys up here, right? S2, S4, S5, C0, C1, and C3, and we reduce it down to array of 3. So let's paste these boys in and just double check. So we was able to get rid of all the W's. And the 3's got replaced with a translation. And then all the W fields yeah, then all the W fields basically got removed, right? So let's double check. Because it isn't there's negates happening here. Oh yes, these got rid of. That was simple. Because these are the W's where it's an implicit 0. So 0 times whatever. These ones you have to keep though, because it's a translation W which has got an implicit 1. So right. That looks fishy to me. Oh no, it doesn't, sorry. Yeah, then we got rid of that. That would have been like take away 0. Okay. This one would have been times by 1, times by 1, and then take away 0. So when we look at it, we also got rid of these guys, right? Alright, let me just quickly undo this. There was something where we changed the C's. Yeah, the C5 became a CZ, is that right? CZ, CZ, CZ. Right, I did do that right. Let me... Okay, put that back. Okay, so basically reduced... Okay, so for the S's, we just made S3, S2. And made it to 3 of those guys. Yeah, so they're basically fine. Crap. My comments up here said C0, 1, and 3. But when I did it in the new, like, it was different from the determinant, basically. I think I removed. So what we should be removing instead was. Yeah, no, I did do that right. It was because I just did a find and replace on those specific ones. Then I thought I brought them down. But we didn't need to bring any down, right? Because it was just 2, and we brought the 3s down to 2s. Yeah, I think I did that right because we just replaced them all. But yeah, let's just undo back to when we actually did the change again. Yeah, then we just changed the 3s to 2s and just that's it. We just did the find and replace basically. Okay, so that seemed pretty legit. Probably remove that now, to be honest. Seems pretty legit to me. Let's like recollapse this expression down from this guy. And let's see if we get to this, right? The determinant could have been wrong, maybe. So the C5 got right, so the S's. Oh, this is interesting. Why is that a dot X? It might be. Huh. That could be the problem. I copied this from this guy and pasted it in here, then it was a C2, but it's actually a C5. Right. There's a problem. Hopefully that's it. So let's resimplify this guy. And that should be good. So we'll obviously have to delete this in a minute. But yeah, so the 2, 4, and 5 get replaced with something more simple. And the S's, so let's start with the S's. So we need to get rid of S2, 4, and 5, and whatever they multiply with, because they're basically zeros. S2 multiplied with C3. S4 multiplies with C1. There's a minus, then a plus. So you would have taken away 0, then plus whatever. So you just get rid of the minus. Then the S5, right? So the S5. Okay, is that good? So now we simplify this. So the C2. Have we got C2? C2 is that. AC. Yeah, so sorry, that S3 needs to go to an S2 now because we deleted the S3. Yeah, so it was 0, 1, and 3 that are left, and now we just bring that down to 2, and then just got an array of 3 floats. The C4 and 5 just get replaced with these guys respectively. And that should be the fix. And that'll be amazing. So now we can just get rid of this. Get rid of that. And fingers crossed. That'll be it. Yes, it worked. So we went from local space to world space to view space, and we invert the matrix and put it back into local space. So, amazing. Let's put a bit of rotation on that. M pi divided by 2. And let's just, hopefully that ends up working, right? Okay, so as you see, these numbers changed. And these scale ones also changed as well in the final matrix. In that final view from local matrix, probably just delete that. But yeah, went all the way from local world to view space, and then it went from view space back to local space, all fine. So let's just quickly again change these numbers to something else. Let's do 77, 12, and 84. Maybe just actually 56, I don't know. Just something different. Okay, so we're back with a margin of error, which is fine. Awesome. That's amazing. So we have ourselves a transformation matrix now. So we should be able to get started on the camera work. So what we have is this model, and ideally we just want to like follow this model. Bossian, thank you so much for the sub. Appreciate it. Welcome. Appreciate the sub, my friend. Thank you, thank you. So if you want to get access to the code, since you subbed, you should just be able to join the Discord channel. And if you've linked your Twitch account, you should just be able to get access to the code. The instructions are, if you follow that link, you can find it. But yeah, if you guys want to get access to the code that was just written, if you support via Ko-Fi or on Twitch, and then follow that link, you'll be able to get access to the code when I upload it at the end of the stream, and it runs on Windows and the Linuxes as well. Right. So with this transformation matrix, we can now do all the maths we need to have a camera that follows this guy. And we can also make it so that we can have multiple models, instances, and all that stuff. But it's going to take a bit of work. It's not mountains amounts of work. We just have to change like probably about 8 shaders to get it all fully working. Why do I have to change 8 shaders? Because we've got like 3 different versions of sorry, we have to change 6 shaders around about, because we've got 3 different renderers running at the same time right now. Right, there's a tile. They all are ray tracing. There's 3 different acceleration structures. One's a tile binning, so it bins into the screen space. Tiles, there's Froxel binning, so it views into screen space. Sorry, frustum space voxels, so Froxels for short. And then we've got a BVH that we bin into. So the binning shaders will need to transform into a certain space, and then in the ray tracer they'll need to transform into a different space as well. But yeah, we probably wanted to set up like a camera, with some field of view parameters with a matrix in there, and have ways of getting like an up vector, a right vector, and stuff like that, which shouldn't be too difficult. We might not need those, to be fair, so I might skip those. And then we can basically hook up controls. We'll start off with one renderer and then work on the rest of the renderers. That should be pretty sweet. So yeah, things are coming together. It's pretty cool. Yeah, I got a jam now because kind of should just go to bed at a good time. I could get started on this now, but we could probably get somewhere today, but I think I always want to get good sleep, to be fair. So our next be on Thursday at 8 p.m. GMT. Well, we'll probably just get the whole camera thing just done in that session. And then on Sunday, we'll probably get started on the model instances, right? which would be pretty cool. No worries, Jam on Toast. Appreciate you guys coming. Thank you for coming. Let's try Berserker. Yeah, hope everyone has a good rest. Well, good tomorrow and a good Thursday. I'll see you all on Thursday. And yeah, catch you all later. All right. Good night.